and overshoot. Okay, that's the Gibbs denominator. It will be there no matter how many terms you have. So long as there's a discontinuity in the function, you will find the overshoot. And you use the Fourier series extension to approximate the function. Okay, so that's the point of the problem. Okay, let's go to the. Okay, now let's move to chapter number 5, Fourier transform. Okay, we're going to speed up a little bit. So sometimes I'm going to use the slide directly. Now, the Fourier transform actually is a limitation of Fourier series. What do I mean by that? For a Fourier series signal, okay, if you read the contents here, in order to have a Fourier series approximation, the signal, x of t, the signal must be periodic. It has a finite period, t sub 0. Okay, so if we go back to the Fourier series expansion one more time. Okay, if you read it carefully, for a Fourier series approximation or expansion, we need a function s of t be periodic. We need the function be periodic. And the period, fundamental period, is t sub 0. Okay, that's a finite number. What if the function we are dealing with is not periodic? Okay, what if the function x of t is not periodic? Can I have the Fourier series expansion? Or how do I twist the Fourier series expansion a little bit so that I can apply the same concept to the function x of t? Now, actually, the answer is yes. Even though x of t is not periodic, but we can imagine that. It is a periodic function with infinite period. Okay, so that comes with this. Look at this figure here. Suppose originally we asked the x of t be periodic. So the period is t sub 0, right? Okay, now that your function you are going to take care is not periodic, then you can imagine this function has infinite. The t sub 0 becomes infinity. Okay? So you are dealing with a function with infinite period instead. Even though it is not periodic, but imagine that it can be presumed to be periodic by assuming the t sub 0 be a huge, very big number that approaches infinity actually. Then we can apply the Fourier series expansion again. Okay? So that is the concept here. The function we are going to take care, we are going to expand, can be treated like periodic function with infinite series. Okay, so mathematically, how do I deal with this? So let's start from the Fourier series expansion one more time. Suppose I have a periodic function. We call it x tilde of t. This is periodic function. And then this can be expanded in terms of the complex exponential function e to the j n omega sub 0 times t. Okay? And this omega sub 0 is the fundamental frequency given by 2 pi over the fundamental period t sub 0. And the coefficient x of n, that is the projection of the function onto this exponential complex function. Okay? So that's the Fourier series expansion. But oops, when the period approaches infinity, okay, looks like we have a problem here because this period approaches infinity. This will go to zero mathematically if this is a finite number. So we need to make a little bit arrangement here mathematically. Okay? Alright, so let's define the function. Okay, originally we have t sub 0 times xn. Okay, but this t sub 0 now will go to a very huge number. Never mind for a moment. So we define a new function, x of omega sub n equals t sub 0 times xn. And this xn is the Fourier series coefficient. Now this xn has to be discrete. Okay, also for Fourier series expansion, that is discrete frequency. That is the integer, the multiple, times the omega sub 0. Okay? And then we let the delta omega be the fundamental frequency. So this is the tricky part. Let me raise up the screen.